Hello and welcome back. So let's talk about unsteady RANs or URANS. And here we're working with OpenFOAM 12, and we're using the same case that we have used in the previous two CFD cookie and one, which is the flat plate. So our roadmap is this one. We're going to address 4 topics. I want to stress that if you already feel comfortable with this, you can skip these videos. Okay, we don't get offended and get right away, right ahead. Hello and welcome back. So let's talk about unsteady RANs or URANS. And hereafter, we're working with OpenFOAM 12. And as a test case, we're using the same one that we use in CFD cookie 1 and 2, which is the flat plate. So here we have the roadmap to this discussion. So this is the theoretical background, then we move to the tutorial. So we're going to revisit the turbulence modeling problem. Hopefully we're already familiar with this, so we're going to go a little bit fast there. No need to go into details. Then we talk about what is the deal of removing smaller scales. And very important, we're going to talk about steady and unsteady physics to make that distinction, because in my personal opinion, sometimes when I'm teaching this one to newcomers, they get confused about this. What is the physics? What is the solver? So to address a little bit that, and finally we talk about time scale separation, a very interesting problem, and then we move to the tutorials. One thing that if you're already comfortable with these topics, go ahead and skip it. Go right away to the tutorials. We don't get offended. So let's address the first topic. Okay, let's revisit the turbulence modeling problem. So we already talked about this as our starting point in fluid dynamics. I'm not going into details. So these are the equations to resolve every single scale, space and time. Okay. So when we do turbulence model, we are going to introduce, some models here. We're going to do some manipulation to get rid of the small scales, okay, because those are problematic. But in theory, these equations, they don't have models, and we can use it to DNAs to resolve everything. So to show you the exact equations for turbulence models, let's use the incompressible just to simplify sims, okay. And again, these equations, there are some documentation source where you will find that they call it laminar Navier-Stokes equation. That doesn't mean that they're only valid for laminar. They are valid for every single regime. The issue is that in laminar, they're going to give you a good solution. Torus regime, you need extremely fine measures. You need to go fully unsteady, fully 3D to get good solution. That is what we talk DNS. So when we do turbulence modeling, we move from those equations, the exact Navier-Stokes, and we use now the RANS equations, okay? Previous 2 videos, we talk about RANS, steady RANS, okay? So usually you see RANS, okay, is related to steady, but can be steady or unsteady. In this series video, we're going to talk now about URANS, unsteady RANS. I have to stress the theory, setup, and OpenFOAM, whatever software you use is exactly the same. The only thing that changes now, we are resolving for time. So instead of doing iterative marching, okay, we need to do a marching in time. So we need to define time step and so on. But the rest, it is exactly the same. Good for us. I don't need to readdress all the theory, all those videos, more than 20 videos that we did in the cookie, CFD cookie 2. We don't need to do anything. Everything is exactly the same, just time. And remember that at the end of the day, what we're doing is modeling this area here, which is the Reynolds stresses. Okay, it requires modeling. We can use Boolean approximation, or we can solve it using Reynolds stress model. It's up to you. Okay, but this is what we're doing. Also to stress that the quantities here are average. That is the derived coming from the technique that we're using to do turbulence modeling to remove those instantaneous fluctuations that are problematic. So usually those instantaneous fluctuations, random fluctuations, are related here in the notation with the prime over bar is average. So basically this is it, okay? Exact URANS RANS equation. Remember, the difference is just time. Then we have some derived problems due to that averages that we study later. So to remind you about the Reynolds stresses is this tensor here. Okay, you can choose to solve it or to model using the business hypothesis. So let me go ahead here. Okay, this one we already visit this one, so no need to go into details. And if we use the business equation, so approximation, so here we're just, let's say we want to resolve this one, you will have 6 equations for the Reynolds stresses. Mathematically speaking, probably will be the best approach, but it tends to be complex to make converge. We have seen that in a steady, it will apply exactly the same for unsteady. So what we use, and the most popular hypothesis approximation, is just to use the business hypothesis now to model the turbulence. So this Reynolds stress, now it is reduced to this business hypothesis. You see this term here. Later I'm going to talk about this one because it's not derived directly from this hypothesis, okay? But we added now just to satisfy some mathematics, okay? So if you substitute this one in your exact RANS, URANS, you get these solvable equations, where are this, and this is it. Look at that now. Here you have the turbulence, viscosity, and this is the extra ingredient to make everything fit. Okay, that's all. So at the end of the day, what we're doing is just computing this quantity from some other derived quantities, okay? So basically, okay, let's move here, okay? So rewriting the equations, and well, the turbulence viscosity, effective viscosity is the summation of the molecular and turbulent, and our solvable equations. Also, you have this term here, this term. Now look at that, we have K here, turbulent kinetic energy with pressure. No, so these are, we can group everything, and these are normal stresses that arise from the business hypothesis. This is specific one that will have the same units as pressure. So then our pressure will reduce to somehow compute K, and if you don't have that quantity, you can neglect it with no problem, but usually it's better to compute it. And then also approximating mu t. Okay, mu t then is approximated using turbulence modeling. Okay, so we addressed this in the previous CFD cookie, and to compute mu t, there are many models. So you have 0 equation models, 1 equation models, 2 equations, 3, 4, 5 Reynolds stresses, and so on. So here you have a cornucopia of models. Things get crazy. So the 0 equation will be algebraic. So imagine that you know mu t is equal to 1, put it there, and that's all. Then somehow you need to compute K. If you don't have it, you can just ignore it, and so on. So a 1 equation model like the scalar matters that doesn't have K, this one is ignored, but then you can get mu t. There are some models, 1 equations that are based in K. You have it here. Then you have 2 equation models like the K omega, K epsilon, that from the combinations, those 2 variables, you derive mu t, and then you have K, and so on. Okay, so that is the idea. Okay, so look at that, nothing changed. The only thing that changed is now we have time, and we need to deal with that. Okay, our simulations are going to be a little bit longer. Okay, computational speaking, and then we need to fulfill all the requirements requiring stability, but that's all. So to summarize now, and the comparison between exact Navier-Stokes equation, which that is laminar equations. Remember, laminar doesn't mean that they are valid only for laminar. Okay, they can solve any regime. Okay, so usually in literature you will find that this is DNS, called the direct numerical simulation, and then we have the URANS. So look at the similarities. They are pretty much the same. The only difference that you have Reynolds stresses. This is where we need to add the modeling, and look at the overbar. Everything has been averaged. Okay, so that averaging is done to remove small scales, and this is turbulence modeling again. So this is our in this table we have the different models that we can find in turbulence modeling now, and we already addressed RANS. So we're in the top here of this pyramid, which is not a pyramid, but in any case, we are at the top here. Now we're moving for ORANS. So see that as we move down, we're increasing computational cost. Somehow we reduce that mathematical complexity, but as we increase also computational cost, we're also improving the solution, the quality of the solution. Okay, so in this case, that improvement is coming from time. Okay, we add time, we have that extra accuracy that also can give you extra stability. Then you move here, and we start to enter into a scale resolving simulations, meaning that you resolve space and time. And usually you resolve a space and it is three-dimensional, okay? So that's why it starts to become more expensive. And when it comes here, there are many, many approaches. Hopefully, still we're going to keep working with this test case, the flat plate, and I'm going to illustrate it this and less, okay? But now that we address URANS, I think we have all the tools just to address a little bit the theory and the differences between those approaches. So that's all for when it comes to the basic equation. So now let's talk about removing small scales that we talked in the previous section. So how to remove those instantaneous fluctuations. So in RANS, steady RANS, we're making this assumption. Now, so look at that, you have instantaneous value, okay? The blue line here, okay? For those colorblind is the peaks, the line with the peaks here. Okay, so this line, those peaks represent instantaneous fluctuations. Those are the tricky ones. So how do we remove that? Well, let's apply an averaging technique and you get this. So a steady RANS relies on the hypothesis that the orange line, the flat one, is not changing in time. So you can take the approach of steady simulations, a steady CFD, in a physics that is steady or in a physics that can be unsteady with questionable results. But this is the idea, okay? So basically we do a mathematical technique, an averaging technique, and we remove those fluctuations. But then we can have the situation where we have an unsteady behavior. So in these fluctuations that you see, the blue line, you can have another fluctuation, a long period. So you have short-term fluctuations, long period fluctuations that change in time. And this is seen on an unsteady mean value. So this is the fluctuation that we're going to see in a URANS simulation. You are not going to see the instantaneous fluctuations. And very interesting here that it might happen that when you're doing the averaging, okay, you take this signal, your physics, you average that, it might happen that that same averaging can also average your long oscillations, the orange line. And as you can guess, you are not going to see that effect. So that is one of the issues that you have in RANS, one of the consequences of that averaging, that you can remove every scale, even as the flow, it is unsteady. So later we're going to talk about that very interesting problem, okay? But what is important is that in most engineering applications, we're interested in the mean quantities, okay? So many times this steady hypothesis is valid, or even if you are on a steady problem, you can use very large time state to approximate that steady state faster, and it is acceptable. But if your problem is that you need to resolve fluctuation, start to think about unsteady approaches. So the techniques to remove those fluctuations, we have to Reynolds averaging and filtering. Filtering will be less, this, and so on. And Reynolds is what we're doing now with RANS URANS, okay? So those methods, now Reynolds, just to mention something, that it will model every scale that you have, okay? Space. Or can be 2D and 3D, can be steady or unsteady. So you can take the steady approaches, even you have something pseudo transient, okay? I don't want to address that, but that will be more in finite volume lecture, but you can take that approach. When it comes to less this and even DNS, basically you are resolving large eddies, to some extension small eddies as well. Every signal is limited by your mesh, okay? And then these approaches, less this, are intrinsically 3D and unsteady, okay? Here 2D is not valid, steady is not valid, you need to resolve everything, and that's why it's very, very expensive. Okay, so as you can imagine, there are many methods in less this, as well as random URANS that we have seen, and at the end of the day, your goal will be to choose the best method or the less wrong method. But let's be positive, the best method. And for that, you need to know the theory, okay? So previous cookies I talk about, so reference paper, so get familiar with that. You need to get the whole theory, just get the gist of what is happening. Okay, so let's talk about how do we do that averaging in RANS. Now, so it's something called Reynolds decomposition. I'm not going into details. Let me address this fast. Okay, I don't want to go. So it's basically you have these 4 steps. So you split your instantaneous values into a mean, fluctuating quantity. You apply some averaging, apply some rules, okay, and then do some algebra, and you will get your exact RANS equations, and then choose a model and, well, go to the solvables. That's all. So basically, when I talk splitting, the instantaneous quantity, the Reynolds decomposition will be instantaneous quantity. Okay, you can split it as a mean value and then the fluctuation. Remember that this mean component here, we're taking the hypothesis that it doesn't change in time, but you can add t and you will have a variation in time, and you will add that fluctuation on top of that. Okay, so sometimes you will find also in literature that there are some other approaches to do that when you have that unsteady mean. So sometimes they call it triple decomposition and stuff like that, or harmonic averaging and things like that. But pretty much that you have now time there, and that's all. Okay, so I don't want to go into too many details to talk about the averaging. So basically, the averaging that we can use is time averaging or iterative averaging. Okay, so basically take that average. You have different time scales. You put a large t here, a very large time, and by doing this, you are going to remove those instantaneous fluctuations. Okay. By the way, there are different averaging techniques. Okay, so there is spatial averaging. So this is probably more into less depth simulations that will apply something similar like that, ensembling, averaging, and so on. Pretty much all of them can be used, but pretty much everything is based in this kind of averaging. Okay, so let's talk about mean quantities when you do averaging and the mean quantity varies in time. So basically, let's say that T1 is much smaller than T2, and then you have now your time. And by doing this one, you see that the averaging is pretty much the same. But when we do this one, you're going to capture this long period oscillation. You have the short period oscillation, and when you apply this averaging, usually you remove that oscillation, but it might happen that also it can remove also the orange, the mean value, the time variation of the mean. So this spacing, this difference in time scales between T1, T2, okay, is known as spectral gap. Very important. You should have a very clear separation. Okay, if that separation is not clear, the averaging will remove everything, and that is the problem that we can find in URANS. So later, we're going to address this again, but this is the main idea, okay, of why URANS, you don't see all those vectors, all those vortices structures and the breaking of the vortices and so on. It's because those fluctuations have been removed, and also that averaging tends to remove much of the physics that is happening in time. Okay, so when doing also Reynolds decomposition and to get the equations, we'll apply some averaging rules, okay, and these are the specific rules for RANS, URANS, okay. When I say RANS, okay, I'm not going to make distinction from now on between steady and unsteady. It doesn't matter, okay. So you have these rules that you can apply now when you derive your equations, and let's revisit that, okay. But part of these rules, the most interesting one, okay, in RANS we make this assumption also that the average of the fluctuation is 0, the average of the average is equal to the average, which is not true when we move to less dense DNS. Well, DNS you use that, but it's not anymore true. Okay, but interesting rules that you have here is that this one, okay, you have this commutation, okay, of the differentiation operator, okay? A little bit hard to digest, but it's true, it can be demonstrated, but the hardest to digest and the one that gave me the most problems, this one, okay? This average here that you have the integral also can be demonstrated, and okay, I did a lot of research, and this can be demonstrated using looking for something called differentiation under the integral sign. Okay, if you look at that, you will see, and you will get to this, and you will be able to demonstrate that this to some extension is true. Interesting to mention a little bit is that this differentiation under the integral sign was used a lot by Richard Feynman. He didn't work in turbulence, he worked something else, but he used it a lot. I find interesting that quote when it was researching, and all around Richard Feynman used it a lot to solve the most difficult problems that he had. Okay, so pretty much that is all when it comes to these two sections, no, the first and the second one, and then in the next video we're going to address steady and unsteady physics to make some distinction, and then this shows this tiny scale separation, okay, the spectral gap. So before ending this, okay, I would like to address derivation of RANS equations. So let me get out of here, and I think I have this here. Okay, so we have this PDF that you have it now in our repository where we have all the material. So this is a PDF where we're a small explanation of governing equation. I'm not going into details, blah blah blah, just rewriting what is already written in books and many papers and so on. Boom, 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 boom. But let's go here to Reynolds average now, just to clarify things. So the Reynolds decomposition, remember that this can be also in time, okay, what we just talked. A little bit more this larger description or longer description about this kind of averaging. And let me stop here. Okay, well here also we have dependent on time and our averaging rules. So now let's derive the RANS equations. Again, to simplify things, let's take incompressible Navier-Stokes. Okay, so we know that we have two variables, U and P. If you have the compressible, you have also enthalpy, whatever variable you can use, enthalpy, internal energy, or temperature. Okay, you have also that one, and you apply in the same way, but in that case, it's called FAF averaging, pretty much the same. Okay, so imagine that you do this decomposition, mean instantaneous, introduce this decomposition into your governing equations. So we have continuity equation, okay, introduce this decomposition, okay, equal to 0, and apply averaging rules, okay? So you have this one, average your whole equation. So look at your average everything, and when you look at these rules, you will see that the average of the fluctuation is equal to 0, so it goes away, this goes away, do your algebra, and at the end of the day, you get this, okay? It's as easy as that, okay? This is the continuity for pressure, exactly the same, a little bit more algebra involved. Okay, that doesn't mean that it's more complicated, just more algebra. So now we introduce also P. So look at you take your momentum equation, put U and P, apply your averaging rules, and you're going to get this, okay? And also to remind you that, well, sometimes you will find some values here and there, just to remind you that you have continuity, so you can also enforce it. You put it there and you enforce that. In any case, you get this, okay, do some algebra, move this term to your right-hand side. So remember that this term is not being computed. Okay, here we're in velocity, so move it to the right-hand side. So you have this one up to here, our Navier-Stokes equation. Now they are expressed in terms of average quantity, and you have this extra term, a source term to Navier-Stokes. And this is your Reynolds stress that requires modeling, and that's all. This is how you derive your exact Navier-Stokes equation. Easy peasy. Okay, as you can see, not a big deal. So a little bit we talk about this, and now let's address this Boussinesq approximation. So this is our Boussinesq approximation, and basically relates Reynolds stress with the mean velocity gradient. Okay, that's all. So we say Reynolds stress equal to mean velocity gradient. That will be this one. This extra term is a mathematical term. Okay, so basically this is what we have. Remember that also, okay, here is these are the strain rate tensor. Okay, we have it here. Here we're using now vector notation. And K in kinetic Turing energy, okay, Turing kinetic energy is equal to this. So basically, okay, this extra terms comes from here. So let's take a look at this one. If we make this value equal to 0, okay, without this term, you're going to get this one, okay, equal to 0. If you take the trace, by the way, it's important, the trace, the main diagonal. You take the trace of the Reynolds stress, and if you say 0, that is not true. because that trace, by definition, this term here, it is equal to the turbulent kinetic energy. Okay, so if you don't add here this term, you don't fulfill this identity, this equality that it has to be equal to turbulent kinetic energy. So this term added here, it is just to fulfill that, to make the trace of the Reynolds stress equal. Okay, so you make the left-hand side equal to the right-hand side when you take the trace, when you take the diagonal. In this derivation, by the way, you take the diagonal, this goes to 0. Then remember, this goes to 0 also because you need to use this identity here. Okay, when you do your algebra, you will get it, and that's all. Then you get this one, you take your trace, and you make it equal. So that's all. That's why we have that term. As I say, not every turbulence model will compute that case, so it's not a big of a deal if you don't have it. So usually one equation model is parallel matters, you don't have it, but from there it's coming. But just to mention that also one equation models that don't compute that term, it can be approximated using an algebraic approximation relation. So yeah, pretty much that's all. Okay, so hopefully you have now a better idea. We'll revisit. Remember, you need to follow the whole video, just skip everything and move to the tutorial. So in the next video, we're going to address these topics. Again, you can completely skip that. So thank you and see you next video. Bye.